My name is Aref from University of Zurich, and I'm going to present our work in entitled A Comparative Analysis of Modality Fusion Approaches for Audiovisual Person Identification and Verification. It's my pleasure to have a cooperation with Masoumeh, Chapariniya, Teodora, Vukovic, and Professor Volker Dellwo from Department of Computational Linguistics of University of Zurich on this paper. Generally, person identification or recognition in a general perspective has a great role in human-machine interaction. To recognize the person identity, different modalities or biometrics can be applied. For example, some of them are face, iris, hair, and palm print that are physiological. It means that they are in our individual body as a constant feature. But some of them, like a gait, made in interaction with the environment and will be changed during the time. Some other modalities, like voice, has both of these features, both behavioral and physiological pattern. To recognize the identity using this biometric, there is different challenges, such as noisy data, such as non-universality, spoof attack, intra-class variation, and inter-class similarities. To achieve a system that performs good for recognition of the identity, maybe one of the good solution is multimodal pattern recognition. It means that using different biometrics or data modalities together to decision about the identity of the person in each time. In this work, we focused on identification and verification. In the identification scenario, we are facing with a multi-class classifier that in which we must recognize the entire utterance based on the pre-trained classes of different speakers or identities. But in a verification scenario, this is typically a two-class classification that in which we must accept or reject the claimed speaker or identity based on the feature of the test utterance and enrollment utterance. In this work, we used Voxceleb2 as a data set to work and evaluate our proposed method. We use the test section of this data set that are video files in MP4 formats, 23 hours of data, and 118 speakers. That is speech are totally noisy with lots of variation, not only the voice, but also the visual aspect of this data set. For example, different hairstyle, different mode, and also different background. To evaluate the system, we use a threefold cross-validation for dividing the data set into test and a train section. We proposed three different systems: FaceNet just for visual parts, or face modality, and two different systems for voice modality. Our face modality is used VGG Face 2 as a pre-trained model. VGG Face 2 has an architecture of ResNet 15 that's pre-trained on a 3.3 million face image of VGG Face datasets. We fine-tune this model by the images of the Voxceleb2 and make our FaceNet system. However, we proposed two different systems as a voice net. The first one is based on the pre-trained ResNet 19 model that pre-trained on image net dataset, and we fine-tune it using gammatonegram. Gammatonegram is something like a spectrogram to represent the variation of the frequency in the different time. But in detail, the difference of this gammatonegram from the typical spectrogram is that there is something like weighting of the that we used previously, for example, in MFCC for weighting the data from different frequency interval. Using this representation method that depicts the voice signal as an image, we can use a two-dimensional ResNet 19 to fed the gammatonegram and learn the different classes. By fine-tuning this model, we achieved VoiceNet in gamma version. Another system for voice modality was training a one-dimensional CNN from scratch using MFCC feature. That in which we use 5 convolutional layer, 1 polling layer, and 3 fully connected layer. And we achieved VoiceNet by that we said VoiceNet X vector in this situation. The proposed system is a mixing how we can, it was our main question, how we can use different modalities to make a decision. It means that how we must concatenate or mix different modalities to make the, for example, identity vector, and after that classification. We can mix the different modalities in 3 shapes. Sensor level fusion, that in which we can extract different modalities, for example, a frame of the face, and a new representation that we choose gammatonegram as a representation method for voice, and concatenate this at the sensor level together, and after that fed them to our face or voice system. In this situation, we can, for example, make a decision using the entire image that consists of the concatenating form of 2 modalities. However, there is 2 different scenarios that are score level fusion and feature level fusion. In the feature level fusion, as I said, we have different system for each modality. We can make a separate system, train separate system for each modalities, and after that, the final layer of the feature extraction part, not classifier, feature extraction part, we can use the final part, final layer, the information of final layer, concatenate them together, and make a new vector representation that is feature level fusion. Or we can use the final score. It means that the final decision of the value of the neuron in the last layer of our classifier to make 2 different vector to concatenate them together and fed them to a new classifier. In this work, we used a softmax layer as a classifier that consists of a fully connected layer and a softmax layer to fed the input feature in sensor level fusion, score level fusion, and feature level fusion to make a final decision. Our experiment was in 2 different scenarios. The first one is for speaker identification. That's in which we evaluate our system in single modality mode and multimodal mode. In single modality mode, we evaluate each one of the proposed system in as a standalone system. That's for example, for a face identification using our proposed FaceNet, we achieved 96%, the average of 3-fold. For X vector as a speaker identification, 72.67, and for a gamma as a gammatonegram as a feature, speaker feature, 61.64. In the downside of the page, you can see the mixed form or the multimodal system. The left side is facial mixed with gammatonegram, that in which because gammatonegram is we can represent the gammatonegram as an image, so we can mix it with a facial modality in sensor level. That we achieve 93.61 in sensor fusion, 96.24 in score fusion, and finally 98.37 in feature fusion. And we can see that the feature fusion performance is better compared to the others. However, for mixing the facial modality using X vector, we cannot use sensor fusion because face is a two-dimensional data and X vector is a single-dimensional. So we just evaluate in S-score fusion and feature fusion. That we can see that for S-score fusion, we achieve 96.70, and for feature fusion, 98.33. And in both of this evaluation, we found that feature fusion could be better in compared to the score fusion and sensor fusion. However, we evaluate this system in verification task. In a single modality task, we achieved 1.01 for face using just face, using our proposed face net, and for voice, we achieved 5.12 for Voxelep 2. However, to mix these modalities together, we have two scenarios. Again, face net using gammatonegram, face net using X vector.
Aref, you will need to conclude.
Yeah. And here we find that again that we reach to better result in compared to single modality. Yeah, to find out which part of our image are more important for the network, we achieve line visualization, that in which we can find that, for example, for face, the important part of the face are focused by the network. But for voice modality, for example, we can see some other unimportant part are focused, and this is the reason of the error for voice modality. For comparison our results with other works, we can find here into table for a speaker identification and a speaker verification that we achieve the better performance in multimodal mode. We use different strategies and different modalities in this work and evaluate the system on Voxelep 2 for 118. And we find that feature fusion is has the better performance in compared to others in the same situation. And for a future direction, we want to work on using deep lift network as an enhancement method for a speech feature, and using paralinguistic system to as a pre-processing to improve the performance. Thank you so much.